So good morning, ladies and gentlemen. Welcome to the training webinar today about GOM Correlate. We would like to show you different aspects in the free GOM Correlate edition in terms of how to do 2D evaluations for digital image correlation. So the agenda for today, we would like to focus on a few different tests. The first one is a low-speed tensile test. We will go then further to high-speed tensile test evaluation, the evaluation of the notch zone of a 2D test, going further into a 3-point bending test, looking into the evaluation of a shear test according to ASTM, and also going through larger scale DIC evaluations. My name is Markus Klein, and I'm sharing the webinar today with my colleague Markus Möller. First of all, we will answer questions during the webinar in the Q&A tab of the WebEx tool. So if you have any question, please let us know. We will try to instantly answer these. The recording that we are going to do will be available later, as this was a question in the very beginning. So starting first with what is GOM Correlate. So GOM Correlate is the free evaluation software that is used for the evaluation of 3D digital image correlation projects which are recorded and evaluated in Aramis, and also the evaluation tool for 3D motion analysis based on point-wise evaluations. So therefore GOM Correlate is used for, on one hand, the later on evaluation in the office where you do not need to sit in the lab, for example. You can take results, share it with colleagues in other departments or even with your customers. GOM Correlate provides the complete image processing, the inspection, and also the reporting, what you need to prepare your measurement results. The topic for today is, and that is what we are going to focus on, is the free 2D correlation. So therefore, the free GOM Correlate software version provides the opportunity to do 2D image correlation. So you can import images or movie files and do the evaluation of 2D projects, means in-plane testing. We're going through all these different tests that we have shown before, and therefore we want to give you an overview what is possible and show you the workflows in behind. There are different video tutorials available at the moment, so if you have questions to the workflows, as mentioned before, please use the question and answer area in the WebEx tool, or have a look in the different episodes which are available, going from explaining the user interface of GOM Correlate, image acquisition, the evaluation, as well as the complete post-processing in terms of component definition and reporting. These videos will be available on YouTube, so have a look on the GOM Metrology channel over there. Or you can access these videos too on the GOM service area under support.gom.com in the manuals and tutorials area. There is also a download possible then, so that you can store these training episodes locally on your PC. So I'm going to hand over to my colleague Markus, who is going to show you the workflows with these different tests.
Hello and welcome also from my side. Thank you for the introduction, Markus. First, I would like to introduce you briefly to the workflow for the preparation and image acquisition. You can find more detailed descriptions in the episode 2 of the video tutorial series Markus has just mentioned. 2D digital image correlation is an optical method to measure 2D or 3D coordinates based on stochastic patterns. The software can compute the coordinates on the pattern in each individual image or frame of a video. The deformed pattern represents the deformed object. You can then deduce full field displacements and strain from these coordinates to analyze object behavior. In order to have a decent contrast on the specimen, priming is sometimes necessary. You can then apply the pattern with a spray can. At the beginning, you might want to practice on a little piece of paper. You can then spray the stochastic pattern on the object. Once you have the pattern applied, you can use a camera to record the 2D test. The workflow is quite simple. Position the camera at a distance that allows you to cover as much as possible of your specimen. Make sure the camera is looking perpendicular onto the object in both horizontal and vertical axes to avoid pseudo-strain due to the out-of-plane movement of the object. You can then focus the camera. If you would like to determine displacements, you have to scale the images. Typically, just measure the width of the specimen. I show you later on how to reference the scale of the specimen in the software. You can then begin with a test and with a recording of the images. So, I will show you now the workflow for the evaluation of such tensile test, which you have just seen in the video. And for this, I just switch into the software. Here you see the start screen, which you see immediately when you open the software. And the first thing you see here is a new project. You have to have a project in GOM Correlate in order to work with it, and therefore you can also open existing projects on this tile here and also access recently used project, which you can load from here. In addition to this, you can also download sample data showing different applications for GOM Correlate, so surface component, motion analysis. You can play with this data yourself later on. The GOM community provides you with more information about GOM Correlate. So we have here the video tutorials Marcus has mentioned previously, but you can also find a written tutorial for GOM Correlate, and you can join discussions and raise questions in the GOM forum, and you find tips and tricks in the knowledge base. And finally, you have the release notes here, which keep you up to date on the constant improvements we make in the software. So going back to the start screen, I create a new project and the software immediately switches into the inspection workspace. Here you have all the tools necessary for the evaluation. However, on the left-hand side here, you can also access the start screen again, which you've just seen. And you have also a dedicated workspace for the reporting, providing more tools for reporting only. So how do you bring in images? You have to go to File, Import File to open images, or alternatively, you can just use a Windows Explorer. You select the folder here and the images and make sure you have increasing numbers in the images to be able to import it. And now I just select the images and drag and drop them into the software. I choose here deformation images, and the software immediately creates a so-called measurement series. In this measurement series are all images incorporated, and you can now slide through those images in the timeline here at the bottom, and the image mapping right in the center shows you now a specific image on the timeline, which is now called a stage. So the first thing we have to do is we have to create a surface component, which you find on this button here. And during the creation of the surface component, the software finds squared facets in the acquired images and identifies the facets by the stochastic pattern structure automatically over all available image data. However, you can also influence the selection manually if you only want to inspect a certain area. So you see here, I just draw a polygon around the specimen, and I finish the selection by pressing the right mouse button here and choosing plus for the selection. So again, everything is calculated automatically, and you can also deselect this hole here because I don't like this outlier here. So yeah, there's also a circle selection tool, so you can span the circle just around the hole, and you finish the deselection also with the right mouse button by selecting minus. As I have mentioned in the previous video, you have to spray the object to get this stochastic pattern, and in order to check whether you've done a good job, you can check here the pattern quality of the specimen, and you see everything here is green, so everything perfectly well. However, you can also orange or even red areas where this might be indication of not such good pattern. If you would like to find out more about a function, you can click here on this question mark, and the software opens up the corresponding direct help explaining all the parameters you see here in great detail. So you can leave the direct help open and continue working, or you can just close it. But this just works in general throughout the software. And now I can create and close the surface component, and the software now computes the image data throughout the timeline. It takes just a few seconds. We have 40 stages here, but it's done now. And you can see here, everything is nicely computed. And you can also see here, we have a properly defined surface component. And just to make sure we are on the same page, you only have 2D information. There is no information in depth, as the specimen was recorded with only a single camera. And to switch the image mapping back on, you can click this button here, and now the software displays nicely the evaluation data and also your inspection data. So at any point you have the image information and the geometrical information of your test. Talking about coordinate system, the coordinate system by default is put in the center of the image. And if you would like to change the coordinate system, you can click on Create Alignment here. It offers you a variety of different alignments, but for now I would just like to use a 3-2-1 alignment. And here you can change the rules in which you want to compute the alignment. And now I only have to click 3 points for a plane, 2 points for a line, and 1 point for Y. And I can also invert here the directions in order to get a positive coordinate axis. And you can see now the specimen is now aligned with the y-axis in tension direction. Once I have clicked OK, you can also see that it has created the alignment here in the Alignment Explorer, and you can switch at any point in the original alignment or in the just now created 3-2-1 alignment. So you can have several alignments in your software, and you can switch at any point, and all values are recomputed automatically in order to represent this. Now, the first check we can use now is, you find this on this button here, is called Check of All Visible Actual Elements, which means it now offers me all the checks which are valid for the surface component, as this is the only element in the 3D view. And now I can choose here epsilon y strain to compute the epsilon strain in tension direction. You can choose here now the strain representation, whether you would like to have technical strain, true strain, green strain stretch ratio, and you can also decide whether you would like to compute against a fixed value or a reference stage. And again, if you would like to find out more about these parameters, what do they mean, you just open here the direct help via the question mark, and you always will find some detailed answers, even with mathematical background. So I just create the surface component, and it's being computed automatically. And you can see now here the full field strain distribution displayed on top of the image data. And you can see also here a legend telling you what these strain values now mean. In addition to this, you can also do a pointwise inspection with deviation labels, where you can gather some discrete values. So if you press Control and hover with the mouse over it, the software immediately calculates the value at this point, and you can create the label with an additional left mouse button click. So I just place some around here. To exit the function, just click the right mouse button, and you see here everything is nicely computed throughout the timeline. And now I'm actually able to compute a report page to document my findings, which you can find here on Create Report Page. So I can give it a name, and I can also choose the template I would like to use. In this case, I only want to have the 3D data in it, and as we have a tensile test, a portrait format is much more appropriate, which you can change here, even though the report page is not created yet. And you can also still edit your content prior to the creation of the report page. And I can now position my specimen nicely, and the software gives me the dimension of the actual report page, so there is no guesswork here. And I can also now choose whether I would like to insert an image or an entire video or a flipbook. And in this case, I would like to see a video in my report. As I have 41 stages, it should compute a report containing all the 41 stages, and it does that very quickly. And you can see here now the report page has become an element in the Explorer, and in the Explorer all elements appear, whether you create them during your inspection or you have imported them, they're all here. And the nice thing is you can just simply restore the content of a report page into the 3D view via drag and drop with the left mouse button. In addition, you can also find now the report in the report workspace, providing you more tools. Again, you'll find more information in the video tutorial episode 6, dedicated to reporting. And I would like to show you now quickly the export of a PDF. So I just say OK, and the PDF is created in the background, and that actually now contains all the video and all the stages I have created. And if I click on it, it plays the video inside the PDF, and you do not need any further plug-in for this. So it just works, and you can share it with customers, colleagues, and so forth. So this was my first quick demo showing a normal, simple tensile test. I will close my project, and we will continue with the presentation. And now I'm going to show you another tensile test. This time it was recorded with a high-speed camera with 45,000 Hertz. Manufacturers for such cameras are, among others, Photon, Phantom or Shimadzu. And this time I'm going to also show you how to import a video, which is fairly simple. If I switch back to the software, I can go to my folder here, and that folder contains an MP4 file. And the nice thing is you can also just simply drag and drop it into the start screen, and the software creates a project automatically for you. And you can see now here the tensile test, the high-speed tensile test in the timeline, and you can also see that it is tearing apart here, and yeah, as you have seen before. So now one thing, the timeline here is not quite correct, because you can see here it's not so high speed. So you can change at any point the timestamp of a stage, and therefore you click with the right mouse button on the timeline, choose Manage Stages, and here you can with Control and Control A select all stages, and you can edit here the timestamp, and it should start with 0 seconds. And I worked out the step size, which is for 45,000 Hertz, is 0.22222 milliseconds. You click OK, and now the software has changed the timestamp, showing the correct time, which you can also now display via right mouse button on the timeline. So you can see here now the real time displayed for this test, and this is sometimes necessary if you get the footage from some random camera manufacturer. So what do we have to do next is we create a surface component, and again I will just quickly reselect the area. So I just draw a polygon around the area, and I create and close the surface component. And now I'm only interested really in the area prior to the failure here. So let's say I would like to see only this data. So how can I do it? I can select with Shift the area here on the timeline, backwards or forwards, doesn't really matter. And then I can create via the right mouse button a so-called stage range. I just add a stage range, and I close it now. And you can see here I have a range. If I double click on it, it maximizes on the timeline, and you can only see the footage now prior to the part failure. So this is something really nice in order to show just some area of your specimen, and you can do it of course in any test. And you can also have several stage ranges if you want to. So now I'm going to change my alignment, and let me just flip here the specimen. So again, I will create a 3-2-1 alignment as you have seen before, and I create a line, and this is done now. And I could now compute again the strain over all the surface component full field. However, you can also do it section based, and for this I can go to pointwise inspection. I create here a section in viewing direction. I select 2 points, and I use these buttons here. They're called smart creation, so they appear where you have an element, and in order to save some mouse movements, you don't have to click here and here. You just can do it over the smart creation buttons. And now I would like to see the section exclusively visible in the 3D view, and to restore it, as same as report, you drag and drop it with the left mouse button. And now we can actually apply the epsilon y strain again, also on this section. And to see some colors, you can open here the properties window, which is behaving on the selected element, and I can now change the display from legend, and also I get the colors here on the section. And you can also change the scaling to automatic scaling via the right mouse button, and select all visible stages. So now it scales the legend according to the visible stages here in the timeline. And in addition to this, you can also display the section in a diagram. Just make sure you have in the diagram settings value range from 3D legend enabled, and now it does the scaling of the diagram accordingly. And you can see now also here in a diagram the strain on the section building up with a high peak until the failure. And if you would like to document this in a report page, you can do it as well. So if I create another report page, I call this section. You can also choose the template 3D plus diagram, and then you can actually have the 3D content and also the diagram parallelly adjusted here. And the video I'm going to create is now based on range 1, which is now my stage range I have here. And the software now creates the report quickly in the background, and yet again it becomes an element in the Explorer, which you can see here. And the nice thing is, if you have to go to a meeting and you want to take the software with you and you want to share it with some colleagues, you can actually say right mouse button, start from the beginning, and the report is being displayed in full view. You also have like a little bar here to with a play button. You can also influence the speed, and you can flip through the report pages if you have several. So really nice option, I think. And with this, we are pretty much done with the tensile tests I wanted to show you, and we continue with another application. And in the next demo, I would like to show you how you can use dimensional elements to investigate the opening behavior of notches. So in order to do this, I will close my project again, and I import the footage. And in this folder here are images again. And what you can also do is you can import the entire folder just by drag and drop. The software reads out all the images and again integrates them in the timeline. And this is done now. Yeah, here we go. And you can see here, this is the notch I have mentioned. And you can see the behavior of this is that it's vibrating, it's opening and closing throughout the test. and I would like to find out what is going on in terms of dimensions. And as I have mentioned in the introduction to the image acquisition, if you want to measure dimensions or displacements, you have to scale the images. To do that, you click with the right mouse button on the measurement series, go to Edit Creation Parameters, and choose Edit Calibration, Define Scale. And now I know that this distance here of this notch is approximately 3 millimeters. So I click 2 points with Control and the left mouse button from one side to the other, and I enter now the value of 3 millimeters. And if I click OK here, I have now scaled my measurement series accordingly. Of course, you can also use a ruler or something and click any point in the image you want. So, of course, again, we have to create a new surface component for this. And again, it pretty much immediately computes everything over the entire data. However, I would only like to focus on the area around the notch. So I select this polygon, and you can also zoom in to get closer to some boundaries, which is pretty handy. And once you've done your selection, you can create the surface component. And again, it computes everything automatically. Now, in order to check some dimensions, you have to construct them first. So I will go to Construct, Distance, and create a simple 2-point distance. And I create them with a Control and left mouse click on either side. Again, I can use this Smart Creation button here to create it immediately. And I create one also here in the middle, and also one here to investigate the dimensions at the end of this notch. Now, what the software did, and you barely recognize this, it just immediately computed the values for the distances in all stages. And what I can do now, I can introduce you to a new software concept. It's called iInspect. And iInspect gives you the appropriate checks for selected elements. So if I select the 3 distances here, I selected the group, iInspect offers me now the available checks for these distances. And it doesn't really matter if I have 3 or 300. If they are of the same type, you can create them all at once. And now I would like to check these distances against the reference stage. So the reference stage is this one here. It's stage 1 by default. You can also change it. And if I click OK, it computes the distances throughout the timeline again. And you can see here that it's changing, opening and closing. And to see this more clearly, you can use again the diagram, where you can see now the alternating behavior of the distances throughout this test. So the crack is alternating, opening and closing. And if you would like to see now which distance is which, you can just simply select distance 1 here, for instance, and you can see here now the value range of the distance 1. Distance 2 is opening and closing a little bit more, and distance 3 has the highest value, which you might expect as the distance here is at the at the end of this opening. And in addition to this, you can also do this inspection full field. So you can use curves for this. And again, you have to construct a curve if you want to use it for inspection. So I choose here curve, and I create a curve along this area here. Just make sure you click on the surface component. You can create it. And I use another curve here. And I create that one as well. And what I would like to know now is the continuous distance between those 2 curves. And to do that, I can use the construct function distance, continuous curve distance. I select curve 1 with the left mouse button here. I click on the label, and also curve 2. And I create and close the dialog, and now I have computed the distance. And now I can use iInspect again, which you can also call with Control and the right mouse button click at any point in the screen you want. And again, I will check for the distance. Again, I will choose against reference stage in this test, and I click OK, and everything is computed again. To see some colors, you can open the properties window again. You can also do that with the tab key, and I choose now display. I would like to see from legend, and it should also show me the vectors, and I would like to have an automatic vector scaling as well. And if I change the scaling now again to all visible stages, it shows me now the opening and closing behavior based on those curves in full field, having basically a nice visualization of the part behavior. And of course, you can also click some deviation labels if you want to. So whenever you see color in the software, you can create deviation labels on it, and they are computed also automatically, showing you now what is going on with this notch. So you see, it's very easy to create intuitive results and actually understand, therefore, the part behavior. Continuing with my presentation, the next application I would like to show you is our 3-point bending test. Now, a typical 3-point bending test commonly consists of a specimen, which you can see here in this nice image, and 2 support pins on either side, and also a loading pin, which is lowered with a constant force until the failure of the specimen. And due to the nature of this test, you can expect compression strain in the upper region and tension strain in the lower region. And beyond this, typical questions in this kind of tests are: is the strain distribution symmetrically or asymmetrically? Where does failure occur, and why in certain areas? So again, I will go into the software. I will close my previous project, and I drag and drop the images for this test. And here you have the bending test with the loading pin here right in the center, and you can't see really the support pins. They're somewhere here, and this was just only focused on the center area, but you can see here also the crack occurring, and you can also via right mouse button change it back to index to see the number of stages. So we have 11 stages here, and now a trick is in order to create the surface component, you can also create it in stage 11 here, because then you can do the selection nicely around the crack. Zooming in again, so I try to define it as close as I can to the crack zone. And once you have done this, you finish the selection, and you can see now it has actually created around the crack, and therefore it's quite easy. What you can also do is you could decrease here the facet size and also make the point distance more dense to actually have more data available to localize more effects, which happen then obviously locally, and then you can create and close the definition. And you can see now that the reason why I have created this in stage 11 is I can't really see where the crack is, so I just did the selection on stage 11. And now the question would be, what is the strain on this area here? And to do this, I can go to my check button again and choose major strain. And if I just create it, you can see now the strain building up in the area around the crack. And you can also see that this butterfly-like distribution of strain with a hotspot area here. If I do the same for the minor strain, you can see also a similar distribution. Of course, you get different values, but you can also see this butterfly-like shaped distribution of strain around the area of the crack. And this might be an indication why the crack is evolving asymmetrically in the first place, but only might. So you can see it's very easy to create such an inspection, and let's continue with the presentation. The next example we would like to show is a shear test according to ASTM. As you may know, there are many shear test geometries today, and due to the limited time we have right now, I'm not going into more detail for shear. For more information about shear tests, you can find the recording of the webinar Optical Metrology for Shear Tests, which you can find on youtube.com/GOM Metrology. In this demo, I'm going to show you a typical evaluation of a specimen geometry according to ASTM, which you can see here on the right image. The material of the specimen is steel, and the size of the shear area, which is indicated here, is 5 millimeter, and the field of view was 12.5 millimeter by 10 millimeter, which you can see here indicated with this red square. We recommend for shear tests a more rough stochastic pattern. As a background, the facets shrink during the test massively by minus up to 70% due to the high compression of the pattern. So here you see an undeformed pattern, and here you see a deformed pattern, and you can also see here that the facets get compressed and distorted throughout the test, and in order to compensate for this, you can define the surface component in a pre-deformed stage. Now, by default, the facet matching is set to compute against the definition stage. And in this way, the software can compute the facets towards the end of the test. Alternatively, you might also increase the facet size to approximately 25 pixels in order to compensate the facet shrinkage during the deformation of the pattern. Now, I'm going to show you this again live in the software. I will close my project and import the image data. And you can see now the shear area here. Let me just turn this 90 degrees. So like I said, the shear area here is 5 millimeters. So this is this zone here. And also the field of view was 12.5 by 10 millimeters. If you scroll through the timeline here, you can see now the shear appearing here in this center. And also you can see the facets get heavily distorted. So in order to compensate for this, I will select here stage 52, and then I will open my surface component. I will put my parameters back to default, and I will now also do a manual selection just around the area here, around the shear zone. So that saves us a little bit of computation time. So I just will focus on this area here. And if I click now create and close, the software will recompute all the surface component throughout all the images. So here it takes a little bit longer to do that, to find the facets in the images, but we are pretty much already done. So if I slide through this again, you can see the surface component is being computed throughout the timeline, and we're not losing any facets, even though we have a very high compression in the shear area. Now, we can now also check some strains. Excuse me. I will select the major strain again. I will compute the major strain over this shear zone now, and if we just slide through the timeline, you can see the major strain building up in the shear zone with high strain values right in the center, and then rapidly declining towards the boundary of the shear zone. If we do this also with the minor strain, you get a very similar pattern. If I slide through, also strain building up in this shear zone, but then of course we are talking about minus strain, so you have like compression strain up to minus 52% here, and but you can also see similar pattern, high strain in the middle and then rapidly declining towards the boundary of the shear zone. So you can see the facets do get heavily compressed, or the material also do get heavily compressed throughout this shear test. And in addition to this, you can also access inspections over the menu. So here you see all the varieties of different checks you have within the software. And now I would like to compute the shear angle. I just click OK, and again you can see now also on the shear angle this pattern emerging with high values right in the center. And if I would like to now know some more discrete, use a point inspection. I click it with Control and the left mouse button in an area with high values, and then again I can go through the menu to access the shear angle here, and now displaying me the discrete value for the shear angle, and you can see now it's building up and up to something like minus 60 degrees. And of course you can also view this now in a diagram showing you what is going on in terms of shear. So this was quickly a demo showing you what you can do with shear tests, and let's moving on to my last presentation, my last demo. And in the previous demos I have shown you tests with fairly small specimen and patterns. However, you can also evaluate larger scale tests, and we have explained how to create patterns for large objects in the episode 2 of the GOM Correlate video tutorial series. Now, this reinforced concrete beam was set under pressure until it cracked and ultimately failed. You can see the stochastic pattern applied here on the specimen in this video clip. And now the interesting part are not the cracks itself, but the behavior prior to the failure. So, and in this demo, I will show you how you can use strain checks in GOM Correlate to predict where cracks will appear, even though they're not visible to the human eye. Switching back to the software, closing my project and importing the dataset. So you can see now here you have 25 stages. If I slide through, you can see not much going on, but the beam is bending down slightly and then ultimately it cracks. But prior to this, you can't see, we can hardly see anything. If I just zoom in a crack zone and move back on the timeline, you can see that around stage 21, you can see this very thin line, a crack appearing, but prior to this you can't really see anything. So what can I do? I can create, of course, a surface component again, and I will just do it on the center area. So I will select a little square here, select this, and now I would like to compute the major strain again over all data here, which I have selected. So if I slide through this now, you can see some lines appearing indicating high strain values, which may ultimately lead to failure. And in order to see this a little bit better, you can just click with the left mouse button in the legend here. You type in 1% and also, let's say, 0% here, and now you have already a much clearer picture of what's going on. And in addition to this, via the right mouse button, you can also show some extrema to make this also more obvious. So if I slide through the timeline, you can see very clearly high patterns of high strain appearing, and they lead ultimately to the failure in stage 25. So what you can do now is you can see that you can investigate the strain prior to the crack, and this might also be an indication why the part failed where it failed. So this was my last demo in this webinar. Thank you for your attention. And we continue with Markus Klein, who has got some more information for you about GOM Correlate.
So thank you, Markus, for showing us how all this works in GOM Correlate. I would like to finish the webinar for today with a few more words. There were a few questions coming up regarding can I get the slides and get the presentation. So the webinar is recorded and a video will be available on our YouTube channel on GOM Metrology, as well as a download available on the GOM service area later on. There is, of course, also further additional documentation available on the service area. So if you go there, log in, you can download the manual actually, which have a little bit more content than the video recordings. If you're interested in further investigating in GOM Correlate, thinking about that the training might make sense, please check our homepage on gom.com on the training area. So therefore there will also be trainings offered to work with GOM Correlate. In addition, there is a GOM Correlate microsite available where you can find the software as a download. There are basically 3 different versions. One is the free GOM Correlate version that you have seen today for 2D image correlation and the evaluation of 3D data. There is a professional version supporting all the features available, including traceability and other possibilities in terms of the evaluation functions, and an enterprise version, which basically is a network license that can be included in your server installation. So there is actually another webinar coming up on the 8th of June where, and Markus mentioned that before, where we want to focus on point-wise evaluation. That is a second topic that we are investigating here due to the reason that GOM Correlate supports on one hand image correlation and on the other hand also motion analysis, point tracking if you want so. So feel free to register. This will be available in a few days on our homepage, and you can register for that webinar too. There was another question coming up during the webinar, whether the image series are available that we used during the different project definitions here today. So on the GOM Correlate microsite and also in the GOM Correlate software in the installation, there is sample data available, which gives you an insight into 2D projects, but also containing a few 3D projects. On the other hand, we will upload these image series and the video files that we have used today a little bit later on to the GOM Correlate microsite. So please feel free to check that regularly to get also these files if you want to use these for your evaluations. So thank you very much for today. We will stay tuned for a few more minutes in terms of you having questions. Have a good day and see you later on.